All right, guys, let's start the next chapter, right? So this is the now third lesson, right? Not the next chapter. Third, number one only, which is your solving linear system for financial applications. So we are still doing your introduction to your linear algebra and matrix operations. And in that introduction to linear algebra and matrix operation, we are trying to do solving linear system for financial application, right? So uh, again, this is one of the most important foundations of quant finance. Most students think that linear algebra is just matrices. Wrong. In quant finance, linear algebra is the language of modern finance. Almost everything in quant finance eventually becomes a kind of linear system or some extension of it, right? So that includes your portfolio optimization, your risk model, your factor investing, your machine learning, your derivative pricing, statistical arbitrage, Monte Carlo calibration, PCA, yield curve construction, XVA systems, neural networks, right? So this chapter is deceptively simple. You're not just learning your matrices, you are learning how institutions mathematically represent your financial reality. Okay. So let's start, guys. Let's dig deeper and start, right? So in this chapter, right, we are trying to understand or solve, right? In fact, we are trying to solve linear systems or financial implications, applications, and then we'll look at your introduction to your linear system, right? So first of all, let's try to understand what exactly is a linear system. I'm pretty sure you already know it, but just reiterating, right? A linear system is a collection of equations sharing unknown variables, right? So mathematically, what is happening, right? You are trying to find values of variables that satisfy all equations simultaneously. Uh, the word simultaneously is extremely important because finance is never one-dimensional. A portfolio manager simultaneously care about your return, your volatility, your liquidity, your factor exposure, duration, convexity, capital constraints, leverage limits. So quant finance naturally becomes or try to become solve many relationships together. This is exactly what linear system do. Why it matters in finance, right? Uh, Again, this part is extremely important because when you look at your portfolio optimization, suppose you have, let's say, 500 stocks, right? Question is how much money should go into your each stock. Those weights become your unknown variable. Now, there are constraints also, right? Because weights, sum has to be equal to 100%, right? Target return has to be achieved, sector exposure has to be limited, beta neutral, volatility minimized, right? This creates a giant system of equation and that becomes a linear algebra, right? So when we are looking at your asset pricing, also think of your CAPM or your comma branch, you're trying to explain returns using your factors, right? You have unknown betas, you have unknown sensitivities, you have unknown exposure, again, linear system, right? Then we are doing for risk management, right? For example, let's say Goldman Sachs, right, had FX exposure, right? Your rate exposure, commodity exposure, right? So now Treasury asks you how much hedge is required. That becomes a kind of system because one hedge instrument affects your multiple risks simultaneously. For example, an interest rate swap may affect your DV01, your convexity, right? Your funding, your liquidity, collateral, right? Again, linear relationships, right? And then we have to do it by matrix multiplication, matrix representation. Uh, the idea is that AX is equal to B, right? A basically is a coefficient matrix, X is unknown variable, B is a constant vector. Uh, Probably the single most important equation in applied mathematics. Matrix A, when we talk about, represents your relationships, your constraints, your sensitivity, your coefficient. A becomes your covariance matrix, sometimes your factor loading matrix, sometimes your transition matrix, sometimes your exposure matrix. Vector X is unknown, could be your portfolio weights, your hedge ratio, your asset prices, your betas, your allocation. Vector B is your target, could represent your desired return, your exposure limits, your cash flow targets, your pricing condition. And you have your deep quantitative kind of insight here. This is how quants think. Reality converted to matrix form, solved numerically. This is your modern quant finance. It's not your intuition alone. Uh, Institutional finance is a matrix representation of economic relationship, right? That we need to understand. Okay. All right. So keep that in mind, right? So A is constraint relationship, C is weight, price, factor loading. B is your targets, which are return, cash flow, and exposure. Okay. Then we get into your next part, which is the methods for solving your linear systems. So again, slide is introducing your three major methods. This is again important because different financial problems require different computational approach. You're looking at your Gaussian elimination. This is the workhorse. Bank use variations of this everywhere. Right? There is a core idea. Again, you have to reduce equations step by step until the solution become kind of obvious. You create zeros below your diagonal entries, right? And see, Gaussian elimination, when you talk about, right, that is systemic row operation, works for most system and is computationally stable. Matrix inversion, when we talk about, right, or you stick to, Gaussian elimination first, right? So what you are doing in Gaussian elimination is basically your objective is that you kind of uh, create zero below your diagonal entries, and it becomes like a upper triangular matrix, and you try to solve it, right? So I will do it step by step. Don't worry ahead. And why it matters, because direct inversion is kind of expensive. Large quant system may involve 10,000 assets, millions of row, real time calibration, right? So efficiency matters. Gaussian elimination is computationally stable, right? Then we have matrix inversion. The slide gives you AX equal to B and use X equal to inverse B. Useful in your portfolio optimization, Markov is. But in practice, it is very dangerous scale. Simple idea is conceptually it looks elegant, right? And the important institution inside here is the real quant tests usually do not explicitly compute your matrix inverse. Instead, they kind of solve directly because inversion is computationally expensive and numerically unstable and amplifies your noise. Right? Very important real world insight, right? Then third is your Cramer's rule. Beautiful theoretically, terrible computationally. You use determinant to solve variables directly. Useful for interviews, teaching, small system, not for real quant infrastructure, right? No hedge fund solves a 10,000 dimensional system using a Cramer's rule, right? So keep that in mind. And we will do Gaussian elimination ahead, guys, so don't worry about it. And all these steps ahead, your matrix inversion also, Cramer's rule also, right? Key point here is that large financial system prefer Gaussian elimination numerical solvent, while inversion and Cramer's rule are mainly used for theory and small example, which I told, right? So remember that part. Okay. Then we have the next part, right? Okay, now here we are getting into Gaussian elimination, right? When you talk about Gaussian elimination, we're trying to go deeper now, right? So see, the idea when we look at Gaussian elimination, please understand very clearly that you look at your elementary row operations, right? So three allowed operations here are your swapping of rows, your multiply of rows, your addition subtraction of rows, and these preserve the solution. Why? Because you are transforming representation, not changing the underlying geometry, right? The deep geometric insight here is that each equation is actually maybe a line or a plane or a hyperplane. Solving system means finding the intersection point, right? Linear algebra is your geometric finance hidden in your algebraic notation, right? So keep that in mind. And then we have forward elimination. This is what I was talking about, that you have to create zero below the diagonal, right? That is what you have to do. You eliminate the lower left, simplify the system. Then we have back substitution, right? The next method, right? And simple idea is that once your triangular form is kind of achieved, you solve bottom variable first and then kind of move upward, right? Why quants care about all the system? Because many algorithms internally use your elimination ideas, your regression, your Kalman filters, your PDE solver, your finite difference method, your optimization engines, right? And this is your foundational infrastructure mathematics, right? That we need to understand. Okay. So this is the example system. Then we have the matrix form, right? And okay, so this is how we progress, right? So this is how we have taken, right? So you see here 2, 1, 1, 3, and then 15. Those are like this. Okay, and then we formally discuss the matrix inversion, right? Now, when we are formally discussing a matrix inversion, please understand very, very clearly that matrix inversion is solving the system, right? Ax is equal to b. If A square invertible, the solution is very simple, x equal to A inverse B, right? Now, the key condition is that A must be square, A must be invertible, meaning determinant should be non-zero. If determinant is zero, there is no unique solution. Financial meaning here is that suppose covariance matrix becomes singular. That means some assets are highly linearly dependent. This happens often in market. For example, two ETFs tracking the same index. When optimization becomes kind of unstable, that is why covariance regularization is critical in quant finance, right? And then we have your Markowitz portfolio optimization. Now, basically, the slide is mentioning your optimal weights require your inverse covariance matrix. That is again massively important. Interpretation is that covariance metric measure how assets move together. Inverse covariance metrics help identify independent risk adjusted opportunity, right? And that is core to your minimum variance portfolio, mean variance optimization, risk parity, statistical arbitrage, right? Again, please understand the inverse covariance matrix is also sometimes called your precision matrix. Why? Because it captures your conditional relationship. Modern hedge fund use this heavily in your graphical model, your sparse portfolio optimization, your network finance, etc., right? Which we need to understand clearly. Okay. In large systems, direct inversion is avoided and numerical solvers are used, right? Once we have done this, we move to the next part. Next part is about Cramer's rule, right? When you look at Cramer's rule, so Cramer's rule solve a square system using your determinants. Please understand what is determinant. Determinant meaning that determinant measures your volume scaling. Determinant measures your invertibility, your linear dependence. If determinant is equal to zero, system collapse dimensionally. Geometrically, planes kind of overlap. Financially, constraints become kind of redundant, right? Now you have to do the real quant connection you have to do for, let's say, for Ax equal to B, the solution for ith variable A, x equal to determinant of A I divided by determinant of A. Then AI is formed by replacing the ith column name with the vector B. Example system is here. So useful for a small system and not efficient for large financial model, right? Please understand Cramer rule is not used operationally, but determinants matter everywhere. When we are doing your stochastic calculus, we are doing optimization, your PD transformation. So conceptually, it is very, very important. Okay. Then once we have done that, we move to the next part, which is your portfolio optimization Markowitz framework, right? So again, we enter the true finance territory here. This is again one of the most important ideas. Objective is that you choose weight, minimizing your risk, subject to your target return. That creates a modern portfolio theory. You kind of, again, we choose portfolio weight to minimize risk or for a required target return, right? When you talk about portfolio risk, right, matrix form, it is like this. Portfolio return constraint is like this, right? W is your portfolio weight. This is your covariance matrix, capture interaction between assets. That's why we have W transpose of covariance matrix, and total portfolio variance is there. Portfolio risk is not sum of individual risks. Correlation matter. That is the entire foundation of diversification. Then we have return constraint, which is like this. Portfolio expected return must equal your target. The real institutional process here is that large asset managers solve your gigantic optimization system daily. Inputs include your expected returns, your coverage matrices, your transaction costs, your turnover penalties, your liquidity constraint, your ESG constraint, your sector cap. This become massive constraint optimization. Linear algebra is the engine underneath, right? Which we need to understand, right? These are all things are given here, and optimization produces system equation via constraint that can solve to obtain your optimal weights. And solving the system gives the best risk-adjusted allocation for a given expected. Then we get into the next part, which is your asset pricing model, multi-factor framework. Please understand in multi-factor models such as your pharma French, right? Your asset returns are explained by your exposure to your risk factors. Okay. And there is a factor model form for an asset I. It is given like this. I've covered this earlier also in one of the topics, right? A matrix representation is like this, right? So, see, this is your institutional grade quant finance going on factor model. The slide gives you Ri is equal to alpha I, beta I1, F1, beta I2, F2. This says asset returns comes from your factor exposure, right? And if you're looking at a Pharma French model, let's say, Pharma French has three factors: market, size, and value. The modern factor also your momentum, quality, low volatility, carry, liquidity, etc. There are macro factors also: rate, inflation, oil, dollar, etc. And there is a matrix representation also, right, which is given here in the matrix representation. This is regression core of a modern quant finance, right? So your X is the matrix of your factor values. Beta are the sensitivities. R is the basically observed returns. The equation which you can see below, right, which is given, this is the least square regression. One of the most important equation is statistic and machine learning. Please understand that this asset pricing model powers your factor investing, your risk decomposition, your alpha research, your smart beta, your hedge fund models, your bar risk models. Even machine learning fundamentally relies on your linear algebra, right, which we need to understand. Okay. Once we have done that, we move to the next part, solving linear systems in practice. This slide is very realistic. Why it is realistic? Because modern quant finance is computationally intensive. And why do we need your computational tool? Because real systems are kind of huge. Covariance metrics for 10,000 assets is what? Right? 10,000 into 10,000, right? That's 100 million entries. You cannot solve manually. Then you have to look at numerical stability, critical topic, tiny errors explode in finance, especially when the covariance metrics nearly singular, assets highly correlated, market stress spikes your correlation. This cause many quant crashes historically, right? And then we look at your institutional reality, real system use your Polesky decomposition, your iterative solver, your sparse mixer method, not a textbook inversion kind of thing, right? So please keep that in mind. Key's insight in practice, you solve numerically rather than manually, right? So again, when we go into your uh, tools used in finance, common tools used in finance, again, Excel, good for your intuition, prototype, small system. Functions are inverse for matrix, inversion, ML for matrix multiplication, right? Used heavily by bankers, but please understand that dangerously at scale, right? Python, this is the modern quant standard. You have NumPy, you have SkyPy, right? One other library which is not given here that is also used. You have Pandas, right? That is also used, right? So this is numpy.linearalgebra.solve for direct solving, numpy.linearalgebra.inverse for matrix inverse. Very, very important. Please understand this is preferred over your inverse. Why? Because internally optimized, more stable and efficient. At Goldman Sachs, JP Morgan, hedge fund, nobody manually computes inverses in the production system. They solve system numerically, right? So the entire chapter basically is teaching you that financial market are systems of your interconnected relationship. Linear algebra provides mathematical language to represent and solve those relationships efficiently. That is why quant is fundamentally matrix driven, your optimization driven, your computational driven, and this is only the beginning, right? Everything ahead, your machine learning, your stochastic calculus, your derivative pricing, your neural nets, your factor investing, AI finance, everything kind of falls there, right? So remember that. Okay. All right. So then we go to the next part, which is your given systems. Again, solving a linear system in Python. Now we're doing your numericals. Now, in this, please understand very clearly, we move from theory to actual quant implementation. This is where students usually realize that quant finance is just not just mathematics, right? It is computational mathematics. This slide is extremely important because this is how your real quant desk works, not by manually solving your equation, but by converting your finance problem into matrix system and solve them programmatically, right? The equation are given 2x plus 3y equal to 8, 4x minus y equal to 7. Matrix form, you are converted into 2, 4, 3 minus 1. You have b, which is 8 and 7, right? And system becomes ax is equal to b, right? Ax is equal to b. So what does it really mean is, this means matrix A contains relationship, vector x contains unknowns, vector b contains your target. This subtraction is everything in quant finance because once a problem becomes ax is equal to b, the computer can solve it efficiently, and the Python implementation is given here. A is equal to np.array 2, 3, 4 minus 1, b is equal to np.array 8, 7, right? And x is equal to np.algebra solve ab print x, right? So again, understand the Python part. Notice carefully they use Python here, not in fact Python np.linearalgebra.solve, not np.linearalgebra.inverse A. Very important because institutional system avoid direct inversion wherever possible, right? We have not used, right? We have not used what? You not use your the idea here is that institutional system avoid direct inversion whenever possible because inversion can be unstable, slow, memory intensive. So Python definitely love this solve thing. Internally uses optimized numerical decomposition method, and this is how large systems are kind of solved, right? So imagine 5,000 stocks, 300 risk factors, 1 million constraint. The same idea scales upward. And hedge funds and banks, Python become the orchestration layer underneath high performance numerical library do the heavy lifting, right? And then we have the financial interpretation that solutions can represent portfolio weight, factor exposure, hedge ratio, and this is exactly kind of correct thing, right? And please understand, and firms like Goldman Sachs and Citadel, etc., the matrix system might represent your cross gamma exposure or volatility surface calibration, your portfolio optimization, liquidity stress constraint, XV adjustment. Mathematics is still same, right? The mathematics will always be this, right? Only scale become enormous, and that's what we need to understand. Okay. Then we get into the next part, which is kind of conclusion here. Conclusion when we're talking about this slide is kind of summarizing chapter. But let's get the deeper story, right? See, first we understand the methods covered. We have Gaussian elimination, which is the operational workforce, transforms system step by step. Foundational for your matrix factorization, regression solver. Then we have matrix inversion, right? Matrix inversion, which is conceptually elegant, useful theoretically, but avoided operationally at scale. Then we have Cramer's rule, beautiful for understanding your determinants, useful in small example, interview discussion, conceptual learning, not scalable. And why this matters in finance? Basically, this part is extremely important because slide says portfolio optimization, asset pricing, risk management. But these are not your separate worlds, right? These are all fundamentally constraint optimization problem, and constraint optimization almost always reduces to solving your system of equation, right? And then we have your next lesson preview. The slide is mentioning your solving large system like your LU decomposition, your Gaussian decomposition. This is where your Quant Finance becomes industrial strength. And why Gaussian is so important? Because covariance matrices are symmetric, positive, semi-definite, and this allows us to get a coverage matrix, in this form, right? The decomposition powers your Monte Carlo simulation, your correlated random variables, your portfolio system, your war engines. And again, this is huge in quant finance, right? The key idea is that efficient linear system solving is backbone of your scalable quant modeling. And that is absolutely true because a quant without linear algebra is like a pilot without navigation system that we need to understand, right? Very, very clearly. Okay. Now we are going to the question, right? When we look at your question, first question is about determining the portfolio weights. Now we move into applied finance example. Again, this is excellent because this is how equation become real investing decisions, right? So when you look at your investor wants W1 plus W2 equal to 1, and you have 0.08 W1 and 0.12 W2, 0.10. The interpretation here is this is a two asset portfolio, right? And asset one return is equal to 8%, asset two return is equal to 12%. Total target portfolio return is like 10%, right? Which we have, and how much would go into each asset is we solve it like this. And first equation is your what is it? First equation, it is your W1 plus W2 is equal to 1. This is called your budget constraint, right? Budget constraint. Right? All capital must be allocated, no idle cash. Second equation is this weighted average return equal to target return. You're solving it. W2 is equal to 1 minus W1. And the second equation eventually becomes W1, W2 is equal to 0.5. Financial interpretation is that equity allocation achieves 10%. Why? Because 10% lies exactly midway between 8 and 12. Deep quant insight here is that this is actually primitive mean variance optimization. Institutional optimization simply adds a covariance metrics or transaction cost, leverage constraint, your sector limits, your liquidity limits, but the heart remains the same, right? Which we need to understand. Then we get into the next question, which is solving for your risk neutral probabilities. Stock can move, okay. 120 or 80, right? Basically, what are we doing here is that we enter your derivative pricing. Slide is again very important conceptually. Uh, we are looking at P plus 1 minus P equal to 1. This simply says probability sum equal to 1. And the pricing equation 120P plus 81 minus P is equal to 105. This is expected value pricing. You're solving it. You are getting P is equal to 0.065. Risk neutral probability of state is 62.5. Again, this is not your real world probability. This is your risk neutral probability. There is a huge difference, right? Please understand, real probability is what market believes may happen, right? Risk neutral probability is mathematical probability making discounted expected price consistent with your no arbitrage, right? And risk neutral pricing is very important for black shows, your binomial tree, your option pricing, derivative valuation, right? Option desk constantly solves system like this. The idea scales into local volatility, or implied volatility surface, or stochastic volatility calibration, all driven by a linear, nonlinear systems, right? So that we need to understand. Then we get into solving for hedge ratio. Again, portfolio payoff equation we look at. This is now your pure risk management, very important for your real finance. 2x plus y is equal to 5, x plus 3y is equal to 7. You make it a matrix form, which is converted here. Solution is x equal to 1.6, y equal to 1.8. These are hedge ratio, meaning how much of the hedge instrument to hold. For example, let's say suppose portfolio has interest rate exposure, your FX exposure, you may hedge using your swaps, your futures, your options. But one instrument affects your multiple risks simultaneously, right? So you solve system, right? And then you look at deep quant kind of risk inside modern risk management is essentially high dimensional hedging. Banks solve enormous linear system daily for your delta hedging, your gamma hedging, your duration utilization, your FRTB sensitivity, XVA exposure offsets, etc. Right? Which we need to know. Okay. Then we have your 16, right? Replicating the bond cash flow, we enter into your fixed income engineering. This is again a core institutional finance. You have x plus y is equal to 100, 1.05x plus 1.08y is equal to 107. Interpretation is you want to construct two bond position replicating your target future payoff. First equation is initial capital allocation. Second equation is about your future value requirement. Solution is given like x and y. Right, and deep insight here is that this is actually primitive cash flow matching, right? A foundational idea for asset liability matching, right? And pension management, your bond immunization, your liability-driven investing, right? Insurance firm constantly solve system to match your liabilities, your pension obligation, your future cash flow commitment, and this becomes your massive optimization. Okay, so that is what we do. Then we get into the next part, right, which is question number 5, which is the arbitrage detection using your linear system. Again, this is one of the deepest slides conceptually because here we have two systems. Your 3x plus 2y is equal to 10, x 6x plus 4y is 20. Second equation is exactly double first equation. So equations are linearly dependent. There is a financial meaning. No unique pricing structure exists. Right. This is extremely important. There is a linear dependence. Right. Meaning one asset can be replicated using others. In markets, linear or markets violate your linear consistency. Arbitrage emerges. This is the foundation of modern derivative pricing, right? And there's a connection to your no arbitrage also here because Black-Scholes itself is built on replication, meaning option payoff replicated using your stock and bond, and that creates a linear system, right? Please understand modern statistical arbitrage strategy look for a pricing inconsistencies for your temporary violation, your redundant structure, and linear algebra attracts or help detect these relationships, right? Which we need to know. Okay. Then we get into question number 18. Q1, a system of linear equation can be written in the form of this. What does vector x represent? Vector x represents your unknown variables. B, right? A contains your relationship. B contains your unknowns. A contains your relationships. X contains your unknowns. B contains your target, right? Question number 2, if matrix A is invertible, solution of Ax is equal to B is what, right? Solution is x equal to A minus 1 B, right? A inverse B, right? Which is this, right? So again, matrix multiplication order matters. Please understand A inverse B is not equal to B A inverse. Matrix are not commutative. Very important. Understand? And then we get into question number Next question, question number 3. You're solving linear system for financial application. In finance, solving linear system is commonly used for portfolio optimization. Why portfolio optimization? Because optimization involves solving for unknown weights under constraint. Exactly linear algebra territory, right? Which we need to know. Okay. And once we have seen this, we get into question number 4. Which method is commonly used to solve system or linear equation numerically? Gaussian elimination, because it forms the basis for your modern numerical solver. Right. And question number 5, in factor model, solving linear system help estimate what? Your factor exposure. These are your betas, right? Values in your factor regression. Please understand this chapter basically quietly introduced the mathematical DNA of your quantitative finance. You learned your matrices, your systems, your optimization, your hedging, your replication, factor models, your arbitrage logic, and these are not your isolated topics. Right? These are all manifestation of one deep idea that markets are integrated system of your equation, and quant finance is the science of solving them efficiently. Okay, so that's what we have, and yeah, and then we have solution, right? Solution explanation, question 1 and question 2. The chapter is reinforcing the conceptual foundation, and honestly, this is where students get confused, and we have solved the answers. So we have already done all this, so you already know, right? We have solved all these things, right? The third and fourth also and fifth also, right? So that is what we have already done. Please keep in mind, go back, revise it. That is what you have to do. Quant finance is essentially inferring the unknown financial quantities, relationships, etc. That we should be very, very clear. Invertibility, you have to understand. You need to understand the portfolio optimization, the classic Markowitz problem, your uh, Gaussian elimination, your factor exposure, right? You need to understand all those. And yeah, so that's how it works, right? So very, very important. Please go back, revise it. Once you do it, I think you will probably find, right? Okay. I'll see you in the next chapter, guys. Thank you.